Hi everyone, thanks for having me. My name is Trey Grainger, and today I'm going to be talking with you about interpreting intent with semantic knowledge graphs. Just a little bit about me. I am the founder of SearchKernel, the AI-powered search consultancy company, and I'm also the CTO at Presearch, the decentralized web search engine. Additionally, I am the author of the book Solar in Action, as well as AI-powered search. And most of the code examples I'm going to go through today to teach you about and show off what you can do with semantic knowledge graphs actually come from chapter 5 of the book. So if you're excited about this topic or interested in learning more, definitely check it out. So to get started, let's just talk about a knowledge graph in general. So a graph is composed of nodes and edges, and a knowledge graph is a graph that essentially models a domain and the information available within it so that you can check with the graph and traverse it and learn and reason about information within your domain. It can be very useful in my field, which is building search engines, to be able to understand user queries, for example. However, building a graph is at any large scale is a very expensive process, and those graphs can be hard to maintain. So we like to automate as much of that process as possible. One of the ways to automate the generation of graphs is to use open information extraction, which is the idea of extracting arbitrary nodes and edges using things like parts of speech, where we take some incoming text, like for example, data scientists build machine learning models. They also write code. We parse that out grammatically to understand the subjects, the objects, and the verbs within a sentence. And then from that, we can learn facts like data scientists build machine learning models and data scientists write code from they also write code and data scientists in the original text that came in. So using this technique, we can extract out information to put into a knowledge graph explicitly from our data using a natural language processing library. Another way to pull out information is to use common linguistic patterns. So for example, there's a type of pattern known as Hurst patterns, which allow you to extract out hyponym relationships or ISA relationships. So given certain types of linguistic structures, I can, for example, pull out that, from up here, that machine learning is a skill, Python is a skill, commute time is a job benefit, those kinds of things by just parsing the text coming in. And ultimately, these can all get mapped in. Microsoft is a tech company. San Francisco is a big city. These could get mapped into this giant graph of essentially taxonomical relationships of sort of hierarchies of what types of things are other types of things. However, there's another kind of knowledge graph, which is the one I'm going to be talking about today, called a semantic knowledge graph. And in this type of knowledge graph, we actually take the text itself and the relationships within the text as the graph and traverse it to find semantically related terms, phrases, categories, etc. So the way a semantic knowledge graph works is very similar to the way we would think of relationships in a structured database. So in a database, we would have discrete values, different kinds of values, but ultimately we have values in fields that can be keys to values in other tables. And so in this case, I can join on a foreign key and understand that the context from the first table applies to the data in the second table for that particular row. When we're dealing with unstructured data, however, this becomes a little bit more challenging because we don't have clear columns and rows. We just have chunks of text. However, if you look at the text actually has significant structure to it. It's just linguistic structure, and it's the reuse of terms across multiple documents. But within text, we've got character sequences that ultimately build up, like ENG, engineer, these all build up to larger terms like engineer, engineers, engineering, which build up to phrases, which ultimately get added to documents and sentences. And so if we can harness these relationships in the semantic structure of our text, we can do some very interesting things. So taking that same text that you saw a slide ago that was just a blob of text or unstructured information, we can actually use the individual words and terms within that text and any other unstructured information like videos or images or audio, and we can actually relate it together. So in this case, you see my name, Trey Grainger, he, his, my name sort of extracted out of this video. Those are all essentially keys or entities that can be joined across these different data sets, in this case, documents. There's also, a name of a conference here, dates, names of companies. These things all, if they exist in multiple different documents, if we can relate them together or join them across those documents, we can pull context from one document into another document and look at that context across our entire corpus of all of our documents. The way a semantic knowledge graph works, or the way it's structured, essentially relies on two different data structures. One is an inverted index, which is a mapping of all of the terms in your document, in your documents, to the IDs of the documents in which they appear. And then what's called a forward index, which is the opposite. It maps all document IDs to a list of all the terms that appear within those documents. So this essentially allows us to start with any term, any keyword, or any combination of keywords, look those up, get a set of documents, and then start with any set of documents and then look up all the terms. By having both of these, going from any term to any document or going from any document to any list of terms, we can actually traverse like a graph through our text. So in this case, I have a skill of Java. So this is the term Java in a field called skill in our document. I can look up all the documents that contain this term of Java, and then from those documents, I can go look up all the other skills that exist within those documents or terms within the skills field. So in my field of work, this is a search engine that has this inverted index and this forward index, though this could be implemented outside of a search engine. But a search engine would be the natural type of structure in which you would typically find an inverted index. And if you're familiar with any open source search engines, Apache Lucene, Apache Solr, Elasticsearch, Vespa, any of these search engines have an inverted index and usually a forward index built into them naturally. So if I can go from a term to a set of documents to another term, then there's no reason I can't go multiple levels deep. So in this case, what I'm doing is I'm starting with the term of Java, finding all the documents related to Java that contain Java, looking for other skills that might be in those documents, finding other documents containing those other skills, and ultimately traversing to a job title. And so I can go as many levels deep in this traversal as I want, but ultimately this structure allows me to traverse from terms to other terms and from those terms to titles, for example. So just to show you some examples of what we can do with the semantic knowledge graph once we have it built, which is as simple as indexing documents into an open source search engine like Apache Solr, which is what my examples are based upon. What I'm going to do is I'm going to index some data sets here. They're Stack Exchange data sets from postings on the Stack Exchange forums. And specifically, I'm indexing the health data set, cooking, sci-fi, outdoors, travel, and DevOps. So once I've indexed those data sets, the first thing I'm going to do is just query the semantic knowledge graph for the term Advil, querying the health data set. And I'm just going to say, return me back the top terms that are the most semantically related to the term Advil. And out of all of the terms, out of every keyword in any of our documents, what the semantic knowledge graph does is it traverses and it finds that Advil, Motrin, Aleve, ibuprofen, another spelling of Aleve, Tylenol, naproxen, and acetaminophen are the most semantically related terms to Advil. And that's actually a nice ranked good list of highly salient terms associated with Advil. I can do the same process with another query. In this case, I'm searching for vibranium. If you don't know what that is, it's a very, very strong and powerful metal, imaginary, made up in the Marvel comics, specifically associated with the Black Panther character, for many of you who have seen that movie. But what I find is that when I search for vibranium, that the terms most closely associated with vibranium are Wakanda, adamantium, and then Black Panther and people from the Black Panther movie. Interestingly, Wakanda is where vibranium comes from, the country, and adamantium is another kind of very strong metal found in the Marvel comics. So still, the semantic knowledge graph is essentially helping us find other very conceptually related terms associated with what we started with, which was vibranium in this case. From those terms, we can then do very interesting things. So in a search engine scenario where I'm trying to interpret the intent of the user, instead of searching for just the text of vibranium across all my documents, what I can actually do is take those terms and use them to expand the query. So instead of running a query for vibranium, I can run a query for vibranium or Wakanda or adamantium or panther or sort of any of these highly related terms and bring back more conceptually driven search results as opposed to just text-driven search results. Another thing I can do, so I showed starting with a query, but you can actually start with an entire document. So in this case, I just made up a fake document here. It just says this doc contains the words Luke, Magneto, Cyclops, Darth Vader, Princess Leia, Wolverine, etc., and a bunch of other words. And I'm going to say that, given that this document is supposed to be about Star Wars, what I want to do is score all of the terms in this document based upon how related they are to Star Wars. And what I actually get back is Luke, Darth Vader, Force, Galaxy, Blaster, Princess Leia, all of the Star Wars related terms scored high in this results list, and then all the other terms scored lower because they are either not associated or have a negative association with Star Wars. And so from there, I can actually take my original document, rank all the terms in it based upon how well they describe the document, and then set some threshold. In this case, I'm going to take anything that scores higher than 0.25, and I'm going to use it to generate one of those expanded queries like we saw in the last example. So in this case, I generate a query of Luke, Darth Vader, Force, Galaxy, Blaster, and Princess Leia with associated relevance weights. I can pass that to the search engine, and then once I've done that, I actually now see results coming back from the search engine for things like, was Darth Vader at his strongest during episode 3? Or why couldn't Snoke or Kylo Ren trace Luke using the Force? Notice none of these have the term Star Wars in them, but they're conceptually related to my original document, and they match based upon the search. So what I've done is I've built a content-based recommendation engine that can start with a document, figure out what's the most important in that document, and then find other documents that are similar. Another thing I can do with the semantic knowledge graph is explore arbitrary relationships. So in this case, this is another superhero reference. Sorry if that's not your domain. I'm going to search for Jean Grey from the Marvel comics, and I want to figure out who she's in love with or who is in love with her. So what I'm going to do is search for Jean Grey, traverse through in love. I'm sort of creating an edge on the fly just based upon that text. And then I'm going to find any terms that are related to Jean Grey through the relationship of in love with. And what I actually get back are Jean and Grey, which, she's obviously going to be in any content related to herself being in love. And then I get Cyclops, Summers, Xavier, and Wolverine. And so if you're familiar with the Marvel comics, you would expect Cyclops and Wolverine to come back because those were two of Jean Grey's love interests. But Xavier might feel a little strange. Turns out that actually Professor Xavier had a thing for Jean Grey. Not a lot of people know that, but it is talked about in the Stack Exchange forums. Therefore, the semantic knowledge graph is able to bubble up that information, even though it's not necessarily common knowledge. And what we've essentially done here is we've started with a note of Jean Grey, found in love with that semantic phrase, and we've traversed through from Jean Grey through in love with to go find these other terms that are pretty much the exact answer we wanted to our question. Again, we've started with just text. These are just single individual keywords. We could run some natural language processing on them to generate phrases or what have you, but we've done no modeling of this data. This is purely text and traversing through the text in our content. Another thing we can do with the semantic knowledge graph is we can classify content, classify queries coming in from users. So for example, if somebody searches for Docker, we can classify them automatically to the DevOps category by traversing from the term Docker to the category field and then finding the top categories. So in this case, Docker gets classified to DevOps, airplane to travel. Interestingly, if I search for airplane and crash as a query, instead of travel, I get sci-fi, because it's much more likely that you'll be dealing with sci-fi content if you're talking about an airplane crashing, because in the real world, airplanes don't actually crash that often, thankfully. Alien maps to sci-fi, etc. And then this one's interesting. If I search for driver, it returns back two categories, travel or DevOps. So if I modify it to be driver and taxi, it gives me the travel category. If I modify it to be driver and install, then it becomes the DevOps category. But interestingly, because this isn't just a classifier, this is a graph, I can actually, after I've traversed to the top category, I can then traverse to find other related terms within that category. So this is a really good way to be able to disambiguate multiple meanings of terms. So for example, if I search for the word server, then it brings me back the DevOps category. And within that category, server means things like Docker, deploy, and SSH. Versus if I look in the travel category, then server means things like tipping or tip, which would be for like a food service worker, or somebody working in a restaurant. But you also see VPN, which is a kind of server that if you're traveling, you would be particularly likely to be using. And so this is not just generating a list of related terms, but it's able to generate them in a very contextual and nuanced way based upon the exact terms typed in the query and the categories and fields within to which you traverse. Drivers, another example here, if I look for driver for in the context of travel, I'm seeing things like driver, driver's license, car, etc. If I look for driver within the context of DevOps, I get things like IPAM, overlay FS, things like network drivers and hardware drivers. So again, a very contextual list of related terms based upon the underlying category, with that category being based upon the context of the query. And so why does this matter if I think about interpreting intent with semantic knowledge graphs? If you're building a search engine or interacting with user queries in any way and you need to interpret and understand them, it allows you to do things like taking this query of top barbecue in Berlin, understanding that Berlin is a location, top is describing some characteristic about the next word barbecue, and that barbecue actually is most closely associated with restaurants, and within that category means things like ribs and brisket. Versus if somebody were to type in barbecue grill, I can take the nuance associated with those words and understand that grill is actually more closely associated with outdoor appliance. That's the category in which it's found. And within that category, barbecue now takes on a different meaning, which is grill, propane, or charcoal, as opposed to ribs and brisket. So this is a great example of how you can use semantic knowledge graphs to interpret the intent of your users. And that's my time. So with that, I say thank you. And if you have any questions about semantic knowledge graphs or how you might use them or building intelligent search engines, please check out my book, AI Powered Search, or reach out to me at trey@searchkernel.com. Thanks so much.